Hello everyone, my name is Jericho, and today I'll be discussing a research paper called Silencing Hardware Backdoors, published by Adam Waxman and Sima Sutomadhavan from Columbia University. So this research explores methods to prevent malicious modifications in digital hardware, which is a growing concern in cybersecurity. So, as cybersecurity threats continue to evolve, hardware security is becoming an increasingly critical issue. So, this presentation will cover the risk posed by hardware backdoors and the challenges in detecting them, and a set of proposed techniques designed to neutralize them. So, before diving into technical details, let's first understand why this research is important. We know that many critical sectors, such as financial institutions, military systems, and other infrastructure, rely on secure hardware. So, a compromised chip could have devastating consequences. However, unlike software, where security patches can be deployed, hardware vulnerabilities are much harder to fix once a device is manufactured. And addressing a hardware vulnerability requires significant effort and cost compared to applying software patches. However, this research offers methods that uses an approach that could potentially save these critical sectors from these threats. It focuses on making vulnerabilities like backdoor intractable for attackers, ensuring that they cannot be activated. But what is a backdoor, you may ask? Well, let's talk about how backdoors work and how they can be introduced into a system. So, a hardware backdoor is a hidden malicious modification in a digital circuit that can be secretly triggered. And with this, it allows an attacker to leak sensitive data, disable a system, or take control of that said system remotely. These backdoors are particularly dangerous because they operate at a fundamental level of the computing system, making them extremely difficult to patch or remove. So, how are these backdoors introduced to a system? Well, this can be introduced from a third party intellectual property or IP. And from there, or from those third party, they can easily manipulate the hardware they are selling to others or providing to others. And through that, they can introduce backdoors to the system of where their piece of hardware is being used. So in the research paper, they used a digital hardware model that is composed of several modules that emulate what is used in the real world, and which you can see here in the left side. And with this model, they broke it down into five interfaces, which you can see in the right side, which includes the global interface, control interface, data interface, test interface, and output interface. With these interfaces, they can pinpoint which ones can be violated by an attack, more specifically by backdoors. So in the paper, they focus on the following types of backdoors. One which is the called time bomb, and the other one is called cheat codes, which is categorized into two separate ones, which is a single shot cheat code and sequence based cheat code. So time bomb or ticking time bomb backdoor is a type of backdoor that activates after a set of time or a set of number of cycles. With this activation or trigger, an attacker does not have to access the machine, which makes this attack so dangerous. As for the interface that this attack it associates with the global interface, as you can see here in the image, which is circled back. And because in this interface, it uses the clock signal to determine or monitor the passage of time or the number of cycles that the system has gone through in its life cycle. And next, we're going to talk about the cheat codes. So this type of backdoors are triggered by data values in the input interface. So, and cheat codes are basically the keys to open the back door. And in contrast to time bomb, cheat codes requires additional attack vector, where an attacker must execute a code on their hardware to provide the cheat code for the backdoor to work. And with that, there are two types of cheat codes. First one is a single shot cheat code. And with this attack, the backdoor is triggered by the single specific input value. And as stated in the paper, single shot cheat codes can be passed to the backdoor to the control and data interfaces. And another type of cheat code is called the sequence-based cheat code. In contrast to single shot cheat code, sequence-based cheat code requires a sequence of inputs from the attacker. So the attacker will not activate until the full sequence has been inputted into the hardware, which makes it hard to detect also during the vulnerability testing. And that being said, these backdoors are difficult to detect, but why is that? Well, first, they lie dormant during testing. As discussed in the previous slides, backdoors only activate under specific conditions, which makes them hidden during a verification process. And another reason why it's difficult to detect them is that the system designs are usually too large to verify. And with the modern chips, which has millions of transistors, it makes it impossible to manually check for every possible backdoor that a hardware may have. So, because detecting these hard backdoors are challenging, this research paper provides a different approach where it focuses on stopping backdoors from activating instead of trying to detect or find them. So, as the research paper suggests, instead of detecting backdoors, we can focus on preventing these backdoors from ever opening. We've discussed how these backdoors work and how difficult it is to find them. So now let's explore the three techniques or methods that can be used to neutralize them. Here we have the three types of solutions that was proposed in the research paper. One is the power reset, second is data obfuscation, and the third is the sequence breaking. So let's talk about the power reset first. This method is used to prevent time bomb backdoors from activating. So what this method does is that it resets the hardware components at regular intervals. Doing this, it prevents them from tracking time that passes or the number of cycles that the hardware components are currently in. With that, ensures that time-based triggers are never activated, which eliminates the time bomb attack. Here we can see an example of a simple hardware description language or VHDL circuit for a power reset. This VHDL circuit is also found in the research paper. So what this code does is it simply counts down from a preset value to zero. Well, of course, if this is used in a real application, the preset value must be lower than what an expected value might be for the time bomb to trigger. Then when the countdown reaches zero, depending on how this reset is used, the hardware system can turn off for one or a few cycles, causing it to reset all registers and other units holding information, which can potentially trigger the time bomb. Then after that, it turns on again. Next is the data obfuscation. This method is used to prevent single shot cheat code. What this method does is that it encrypts the input data before it reaches an untrusted hardware unit. In the research paper, they categorized hardware units into two types, one for non-computational units and one for computational units. And as a quick review, non-computational units does not operate on data values, meaning that they only move the data that are inputted to them. On the other hand, computational units do operate on the data values. So if they take an input, the output will be different. And with that, they introduced two types of data obfuscation, one for non-computational units and one for the computational units. The method introduced for obfuscation for non-computational units is pretty simple. The data will be inputted into untrusted hardware is simply XORed. And once the data is out, it's XORed back again to its original values. And with that, the hardware takes in a completely different data, preventing the activation of the backdoor without completely altering the original data, which you can see here in the image at the bottom where a set of data is XORed and the XOR key is generated outside here, and the XOR value of those two inputs will be inputted into the hardware unit. And then once it's out, it's XORed again by the same RNG key, or like the random generated key, back to its original value. And here you can also see in the image on the right, which shows an example of a VHDL circuit for encrypting and decrypting the data as it passes through the untrusted hardware, where you can see the black box wrapper has these parameters, and within that, there's another black box untrusted, which um simulate the actual untrusted hardware. Then from there, the data is XORed by a random generated number. And then as the data goes out for the output, it's XORed again with the same random value input. Next is the data obfuscation for computational units. Since these computational units that the data is passing through is more complex and actually operate in the said data, we can't really do a simple encryption like we did for the non-computational where we just XOR because it will alter the expected out value. So a recommended solution that the paper discussed or talked about was a homomorphic encryption. So with this encryption, it will allow the unit that is handling the data work with an encryption version of the data values. The downside on this, however, is that it gets really expensive to implement, especially on the systems that are in a larger scale. So with that, as they stated in the paper, a further study is needed. The last method that was talked about in the paper is the sequence breaking method. This method is used for preventing sequence-based cheat codes. And what it does is that it reorders the input data sequence that is being processed by an untrusted unit. Like you can see here in the picture, a certain sequence is being passed, which spell out like cafe, like CAFE, and then it is reordered into CFEA, which is then inputted to the entrusted unit. By doing that, it will not trigger a potential backdoor that is within that unit. But with that, due to memory controllers, some inputs have sequences that needs to be followed, making them not be reorderable. So there's a chance that an attacker or a smart attacker can use this to their advantage. However, in the paper, they implemented another method, which is by adding a dummy data events. So, for example, when a long stream of loads and store that cannot be reordered is detected but is being inputted, a few dummy load is inserted to the stream, resulting in the sequence breaking up, which essentially works the same as reordering. So having both reordering and insertion of dummy loads implemented for this method, it ensures that no sequence can trigger a backdoor. That being said, how are these methods tested? Well, for evaluating their methods, they first set a goal for themselves where their first goal is to determine what the performance impacts of the mechanisms on a typical programs. And the second one is to understand the trade-offs between the strength of security and the cost of performance. And for their implementations, they used the Zesto simulator. Then to implement or to mimic each methods, they implemented some mechanisms to their simulation. So for power reset, they added a mechanism that flushes the processor state, which is parameterized with different time intervals, which simulates the event when the power is being reset and the local states and instructions are being wiped. As for the data obfuscation, they added the ability for caches in memory to stall, which is also parameterized with the number of cycles on each axis. And with this, it simulates the effect of adding an encryption step before the data gets inputted. Lastly, for reordering and insertion, they stalled pending memory accesses in the memory controller before sending them out to the RAM. With that, let's look at the results that they've gathered. So, seeing the figure, which came from the research paper, the methods cost the runtime of the hardware more than 1% performance hit on average, which you can see over here, which is like the black lines. And then looking at the power reset method, which is the second one, it shows the least number of changes where the runtime is almost the same as the baseline, followed by the memory reordering and memory insertion. And with that, we can only see significant changes on the runtime. However, when every method was combined in a single hardware unit. But even with that, the data shows that the runtime only slowed down by an average of just under 0.9% of performance hit. In the next slide, we'll look further in the results from the three experiments, which focuses more on the methods that they discussed. So the chart on the left shows the trade-off between the power reset frequency and the performance loss it produces. With the baseline having 10 million frequency, it showed insignificant performance loss. And we can also see this insignificant performance loss with 50 million cycle and 10 million. And then pushing the frequency to 1 million, like 1 million, there was some increase in performance loss by about 0.3%. But with that, we can say that the power reset does not really affect the performance that much. Next, in the middle chart, it shows the effect of memory insertion frequency to the runtime performance. In this test, the frequency is determined by the maximum number of bits of information that is allowed to go through the memory controller before a dummy load is inserted. With that having only 4 inputs at a time, we can see that it had the most impact on the performance in the chart. However, the performance loss is not that significant, where the performance was reduced only just under 1% on average. Then, as we reduce the frequency down to 32, the performance hit average goes down as well, which shows insignificant impact on the performance. And similarly for the third chart, it shows the effect of the reordering frequency to the runtime performance. Like what we saw with the insertion in the second chart, the less frequent the data is reordered, the less it will impact the performance hit average. Though looking at the chart, compared to insertion, reordering has less impact on the performance hit, where at the frequency of 4, we only see about 0.6% of performance hit compared to the frequency of 4 in the insertions. With that, it shows reordering is slightly optimized than the insertion, but it's not very noticeable. And with the good results that the method showed, as seen in the previous slide or showed in the research paper, they also talk about the coverage it has for a real-world attack. One of the cases they talk about was for the Illinois malicious processor, or IMP. So this processor contains components that can run malicious mode, which acts like a backdoor, which can be triggered by certain deterministic events. One of the attacks that it supports was the malicious memory access. This attack allows any program to access a large portion of memory, and to trigger the backdoor, an attacker can place a sequence of bytes on the data bus. And having that description alone, it works just like one of the attacks that was discussed earlier, which is the sequence-based attack or sequence-based cheat code. And with that, it can easily be defended using the defense mechanism that was discussed earlier, which is the sequence break method. The other attack that the IMP supports is called shadow mode. This attack is turned on or triggered by a bootstrap trigger, which is basically a network packet that tells the hardware or the processor to initialize the shadow mode. And as described, the attack also works like a single shot cheat code, which could be prevented using obfuscation method that we discussed earlier. Lastly, IMP can also be reconfigured to use time bomb attack, but with the reset method, this can also be prevented. And with that, it shows that the methods that were discussed can really be useful. So, conclusion. And for limitations and future considerations, well, while the methods discussed provides a strong defense against deterministic backdoors, there are still challenges in the field of hardware security that needs further research that was discussed on the research paper. One of them is the scalable and unintrusive backdoor protection. So while power resets and data obfuscation can be implemented without requiring knowledge of the hardware's internal design. However, system with large control interfaces like the GPU or the modern CPUs, it still presents a challenge. So if a small control signals are combined, they can form an undetectable backdoor. So future research should investigate methods to identify and protect control interfaces without requiring full access to the hardware source code. Next is the non-deterministic backdoors. So non-deterministic backdoors can include randomized time bombs where the trigger is unpredictable. So further research on real hardware is needed to assess the practicality of these attacks and develop corresponding countermeasures, just like the methods that was discussed on this research paper. Another challenge that needs a further research on is the side channel induced backdoors. So while the proposed methods assume that the triggers must pass through the standard input interfaces, attackers could also use side channel signals like power fluctuations or electromagnetic emissions to trigger or activate the backdoors. And lastly, one of the future considerations that was also mentioned in the paper is the real world implementation and testing of the discussed methods, which are the power reset, obfuscation, and the reordering. So while the methods were tested through simulations and showed good results, um, real world hardware implementation is still needed to verify its usefulness and effectiveness. So future studies should focus more on prototyping these methods of defense across different hardware architectures to ensure broad applicability of those methods. And with that, for the final thoughts, well, as cybersecurity threats evolve, hardware security should also be researched extensively. We usually focus on software vulnerabilities, but without secure hardware, a computing system is still at risk of attacks. And with that, thank you for your time.